We're now going to extend our results from the one-period binomial model to the multi-period binomial model. We'll see that our results from the one-period binomial model actually extend very easily to the multi-period model. So let's get started. Here's a three-period binomial model. It's actually the same three-period binomial model that we saw a while ago when we had our overview of option pricing. We start off with a stock price of S0 equals $100. We have a gross risk-free rate of R equals 1.01 per period. We assume that in each period the stock price goes up by a factor of U or it falls by a factor of D. So U is equal to 1.07, so stock price goes up by a factor of U to 107, or it falls down to 93.46. Now the true probability of an up move is P, and the true probability of a down move is 1 minus P. But we also saw in the last module that P and 1 minus P don't matter when it comes to pricing an option. As long as, in fact, and this is a subtle point, as long as P and 1 minus P are greater than 0, and there's no arbitrage, we determined that there were Q and 1 minus Q also greater than 0. These guys are called the risk-neutral probabilities, and we saw that we can use these probabilities to compute option prices. For example, in our one-period model, we saw that we can compute the price of a derivative as being equal to 1 over R times the expected value using these risk-neutral probabilities of the payoff of the derivative at time 1. Okay, so we're now in our three-period binomial model. We want to be able to price options in the three-period binomial model. And we can easily do that using our results from the one-period case. Because the central observation we want to make is this multi-period, or in this case three-period binomial model, is really just a series of one-period models spliced together. So for example, here's a one-period model. Here's another one-period model. And here's another one-period model. So in fact, from t equals 2 to t equals 3, there are 3 different one-period models, only one of which will actually occur, but there are 3 possible one-period models. Likewise, at t equals 1, there are 2 possible one-period models. There's this model, and there's this one-period model. And at t equals 0, there's only one one-period model, and it's this one. So in fact, we see we've got 6 different one-period models in this three-period binomial model. And what we can do is we can use our results for the one-period model that we developed in the last module on each of these 6 one-period models. So in fact, that's what we will do. Okay? So what we have is we saw that if there's no arbitrage in the one-period model, we know there are probabilities Q and 1 minus Q. These are the risk-neutral probabilities that we can use to price an option in this one-period model. Well, the same risk-neutral probabilities will occur or can be used here and here, and likewise there and there. Remember, each of these one-period models is essentially identical. The stock price goes up by a factor of U or it falls by a factor of D. It's the same U and D in each of these one-period models. It's also the same gross risk-free rate R in each of these models. So in fact, they'll have the same risk-neutral probabilities. U is equal to R minus D over U minus D. So in fact, since R, D, and U are the same for all of the one-period models, all of the one-period models have the same risk-neutral probabilities. Q, 1 minus Q, Q1 minus Q, Q1 minus Q. And indeed, it's true also at time t equals 1. Q, 1 minus Q. And of course, these are the true probabilities. Well, let's erase them. And let's replace them with the risk-neutral probabilities Q and 1 minus Q. So in fact, this three-period binomial model can be thought of as being 6 separate one-period models. If each of these one-period models are arbitrage-free, and we recall that will occur if D is less than R is less than U, then we can compute risk-neutral probabilities for each of the one-period probabilities, and then we can construct probabilities for the multi-period model by multiplying these one-period probabilities appropriately. Suppose, for example, I want to compute some risk-neutral probabilities in this three-period binomial model. How can I do that? Well, let's create some space here and let's get rid of this stuff. Okay. let's compute the probability, the risk-neutral probabilities, let's call them Q, of arriving at each of these terminal security prices. So how about this point here? What is the risk-neutral probability of the stock price being equal to 122.5? Well, the only way the stock price can equal 122.5 is if the stock price goes up in each period. It has to go up in every period. The probability of it going up in every period is Q times Q times Q, and that's Q cubed. How about at this point here? What is the risk-neutral probability of the stock price being equal to 107 at time t equals 3? Well, in this case, it's actually going to be 3 times Q squared times 1 minus Q. Now, how do I know that? Well, let's think about it. There are actually 3 ways to get to 107. One way is for the stock price to fall initially, and then to have 2 periods where it goes up. A second way is for the stock price to have 2 periods up, followed by 1 period down. And a third way is for the stock price to go up, then to go down, and then to go up again. So there's 3 such paths through the model where the security price at time t equals 3 can end up at 107. Each of those paths requires 2 up moves, which occurs with probability Q squared, and 1 down move, which occurs with probability 1 minus Q. So we get Q squared times 1 minus Q, and there are 3 such paths, so we get 3Q squared 1 minus Q. Okay, it's the same for 93.46. There are 3 ways for the security price to get to 93.46. It can go up and then have 2 down moves, it can have 2 down moves and then 1 up move, or it can have a down move, an up move, and then a down move. So in fact, this occurs with probability 3Q times 1 minus Q squared. We have 1 minus Q squared now because we need 2 down moves, and the down move occurs with probability 1 minus Q. Finally, the stock price can be 81.63 only if we have 3 down moves in a row, and that occurs with probability 1 minus Q cubed. Okay, you might recognize these probabilities as being the binomial probabilities. Okay, so the binomial probabilities will say that the probability will be n choose r times q to the r 1 minus q to the n minus r. In this case, n is equal to 3, and r is the number of up moves required. So if r equals 3, then we must have 3 up moves and we get q cubed. If r equals 1, then we have 3 choose 1 equals 3, and we get this number here, and so on. So now suppose we want to price a European call option in our 3-period binomial model. We're going to assume the strike is $100, and therefore the payoff of the option at time t equals 3 is given to us here. It's 0 and 0 on the bottom 2 nodes. This is because the strike is $100, which is greater than the stock price at these nodes, so you wouldn't exercise and you would receive 0. If the stock price ends up at 107, you would exercise. You'd get 107 minus 100, which is $7. Likewise, up here, you would receive $22.5. And now what we want to do is figure out how much is this option worth at time t equals 0. In other words, what's the fair value or arbitrage-free value of this option? Well, we can do this simply by working backwards using what we know about the 1-period model. So we know how to price options in a 1-period model. We saw this in the last module. We're going to do this here as well. So what we can do is we can start at time t equals 3, okay, and we're going to work backwards. From t equals 3. So what we can do is we can actually start with this 1-period model here. So let's take a look at this 1-period model and just figure out how much is this derivative security worth at this node here. This is a 1-period model which pays off 7 at this node, 22.5 at this node. We can compute the fair value of the security at this node. We can do that using our 1-period knowledge. We can do the exact same for this node, Okay, we can treat this as a one-period model, compute the fair value at this node, and also compute the fair value at this node. Okay, so by working backwards now, we can assume we know the option price at this node, and this node. And now we can do the exact same thing. We can now go from t equals 2 back to t equals 1. In this case, we've got two one-period models. Here's one of them. We know how much the option price is worth there. We know how much it's worth here. So we can figure out how much it's worth here, again, using our results from the one-period theory. Likewise, in the one-period model here, we can do the same thing. We know how much the option is worth at this node. We know how much it's worth at this node. It's already calculated. And we can use our one-period knowledge to figure out its value at this node. Finally, we can go from t equals 1 to t equals 0. And again, we want to compute the value of a derivative security with a payoff of this quantity at this node and this quantity at this node. And we can actually compute the fair value of this, again using the risk-neutral probabilities, to compute its fair value here, which we would call C0. So that's all you have to do. Right, we can splice our one-period models together. They're all arbitrage-free, as we said, because D is less than or is less than U. So there are risk-neutral probabilities in each of these one-period models. So what we can do is just work backwards, starting off with the final value of the option at t equals 3, figure out how much it's worth at the nodes at t equals 2, using our one-period theory, going from t equals 2 back to t equals 1, again using our one-period knowledge, and from t equals 1 back to t equals 0. And here are the calculations. So I haven't actually done the calculations here, but there is a spreadsheet that you can download with this module, and in the spreadsheet there'll be a particular worksheet which will actually have these calculations, as well as the formulas inside the cells which will do these calculations for you. So what you'll see is we're actually calculating these quantities according to the one-period model. So for example, let's take a look at this one-period model here. I know that the 15.48 over here is equal to 1 over R times Q of 22.5. So Q times 22.5 plus 1 minus Q times 7. This comes from our one-period theory, and of course Q is the risk-neutral probability of an up move. It's equal to R minus D over U minus D. And of course in this case, U is equal to 1.07, D is 1 over U, and R was equal to 1.01. So you can actually check these calculations in the spreadsheet. If you like, you can have the spreadsheet open while you're going through this module, and you'll see the formulas in each of the cells showing these calculations. So what we're doing is we're working backwards. So the cell here at this point in the spreadsheet will have exactly this formula here. Likewise, except it won't have 22.5 and 7, it will just refer to the cells containing 22.5 and 7, and it will be the same formula repeated throughout the spreadsheet. So that's how we compute the value of the option, and its fair value at time 0 is 6.57. And it's important to keep in mind that this is the arbitrage-free value of the option. The way we calculate this value is by using our one-period knowledge and working backwards one period at a time. But in fact, there is a faster way to do it. We can use what we did in the previous slide where we calculated these risk-neutral probabilities. Okay, so these are our risk-neutral probabilities. You can easily check that doing this backwards calculation, working backwards one period at a time, is actually the same thing as doing it all in one shot. So instead of doing a calculation coming back from t equals 3 to t equals 2 to t equals 1 to t equals 0, I can do it as just one calculation, okay, where the call price at time 0 C0 equals 1 over R cubed. So this is our discount factor. It's cubed because there's 3 periods. And it's the expected payoff of the option, which is ST minus 100, and the maximum of that in 0, under these risk-neutral probabilities here. So I can do it in one shot. So basically, working backwards one period at a time, you can check is it the exact same thing as doing it all as just one calculation like this. Okay. This is risk-neutral pricing in the binomial model. It avoids having to calculate the price at every node. And by the way, you can compute any derivative security in this model this way. You can compute the payoffs here at t equals 3 and use risk-neutral pricing in one shot like this. So for example, let's create some space here. So, okay. Suppose I want to compute a derivative security which has payoffs C, let's call it, okay, so let's call it C of 122.5. So this is the underlying security price at this node. C of 107, C of 93.46, and C of 81.63. Okay, so this could be the derivative payoff C3. There's some value at time t equals 3, and its value depends on the security price at t equals 3. So it could be a call option, a put option, or some other funky security. Then I can calculate this price as 1 over r cubed times the expected value using these risk-neutral probabilities of C3. Okay, and it's exactly the same argument we use for the one-period model. I could work backwards one step at a time to compute the value at each of these 3 nodes. Once I have those 3 nodes, I can work backwards to these 2 nodes. And once I have the value at these 2 nodes, I can work backwards to get the value here. Or I can do all of that in one shot via this calculation here. The spreadsheet does it by working backwards one period at a time, and you can see the formulas in there and confirm that all we're using are the one-period risk-neutral pricing formulas. Okay. Another question that arises is down here. How would you find a replicating strategy? We'll address this question as well as defining what a replicating strategy means in another module that we'll see very shortly. We're now going to return to a question that I raised in an earlier module. That question concerned the following situation. We had a one-period binomial model, and we had 2 securities that were absolutely identical except they had different probabilities of an up move. The first security had a probability of 0.99 of an up move. The second security had a probability of 0.01 of an up move. We argued, however, that both of these securities had the same option prices, and we found that to be somewhat surprising. Well, we're going to address that issue in this module, as well as some other questions that are also of interest. So if you recall, we had the following situation. We had 2 securities, stock ABC and stock XYZ. The 2 stocks were identical in every way, except they had different probabilities of going up and going down. Stock ABC had a probability of going up of 0.99 and a probability of going down of 0.01, whereas stock XYZ had these probabilities flipped. The probability of going up was 0.01, the probability of going down was 0.99. And then we talked about a call option with payoff equal to the maximum of S1 minus 100 and 0. Okay, and we wanted to know how much a call option was worth on each of these 2 stocks. Well, the strike is 100, so the payoff here would be 10 or 0 in each case. So this is the payoff of the call option, C1. Probability of a payoff here is 0.99, and down here it's 0.01. So it stands to reason that the value of a call option on this security with a payoff of 10 with probability 0.99 should be worth a hell of a lot more than a payoff of 10 with probability 0.01. Well, if you believe the theory that we've developed so far, then that is simply not true. Assuming you can invest or borrow in the cash account at a gross risk-free rate of R and that you can buy or short sell the stock, then in that case, the call option in both cases must be identical, and it turns out to be approximately $4.8. So C0 is approximately $4.8 here, C0 being the fair value of the option price at time 1. And C0 down here is also equal to $4.8. And so this seems very strange indeed. And a lot of people get upset with this idea. They feel something is wrong with the theory when you can have a situation where 10 with probability 0.99 is worth $4.8, but also 10 with probability 0.01 is also worth $4.8. And so it seems like there's some sort of contradiction or something strange going on here. And we're going to resolve that issue by reminding ourselves, first of all, of our one-period theory. In our one-period theory, we saw that the fair value of the option C0 is equal to 1 over R times the risk-neutral expected value of the payoff. So that's this quantity here, where the risk-neutral probabilities are given to us by that quantity and this quantity, U minus R over U minus T equals 1 minus Q. And of course, we see that the true probability P, well, it just doesn't seem to appear everywhere. The only assumptions we made about P was that P is greater than 0 and 1 minus P is greater than 0. Likewise, with no arbitrage, we know that D is less than R is less than U, so that Q is greater than 0 and 1 minus Q is greater than 0. Okay, so it appears that P does not matter. And this is the source of confusion for a lot of people. But in fact, it only appears surprising because we are asking the wrong question. So the question we are asking is, why is an option in this model worth $4.8 and it's also worth $4.8 here? That's not the right question to ask. The right question to ask is, why would you find a situation like this in an economy where there's a stock with probability of 0.99 growing by 10%, and in the same economy that you would find another stock which would have a probability of only 0.01 of going up by 10%. These stocks are incredibly different. You would never expect to see two securities like this in the same economy. So your problem shouldn't be with the option pricing theory and why you get these two option prices being equal to one another. Your question should be, why would you ever expect to see two securities like this in the same economy? This is the source of the problem, assuming that you could find two stocks like this in the same economy. I've never seen this situation myself. I've never seen any situation like this, and I can't imagine a situation like it happening. But if you did find yourself in an economy where you had two stocks, ABC with this characteristic or these characteristics, and stock XYZ with these characteristics, then indeed you will see that the option prices in on the two securities will be the same. And so the source of confusion is resolved by focusing on why you would see these two securities and not by focusing on the option pricing theory. The option pricing theory simply states that if you do have two securities like this in the economy, then they will have the same option price. Okay. On this slide, I want to discuss another interesting example. Consider the following three-period binomial model, which we have here. The stock price starts off at S0 equal to 100, and it goes up by a factor of U equals 1.06, or it decreases by a factor of D in every period. The gross risk-free rate is 1.02, and we want to price a European call option with strike K equals 95. So the way we do that, as usual, is we determine the payoff of the option at maturity. So the maturity is at T equals 3, and this is the payoff of the option. It's 24.10 if the stock price is 119.1, 11 if the stock price is 106, and 0 in the other two states. Okay, so note that this cash flow is non-negative, and it's strictly positive in these two states up here. Okay, and we can price this option using our knowledge learned to date, and we can find out that the option price is equal to 11.04. Okay, let's price the same option again, but this time we're actually going to change the risk-free rate. We're going to change it from 1.02 to 1.04. Everything else about the option is identical. We've got the same set of cash flows at maturity at T equals 3. We can work backwards in the lattice, compute its price, and if we do so, we'll find the price is equal to 15.64. So in the first case, when R equals 1.02, we find the option price is 11.04. In the second case, when R equals 1.04, we find the option price equals 15.64. Now this is a little bit surprising because what we've done here is we've computed the value of this cash flow by computing its value today t equals 0. And we've discovered that when we increase the interest rate, the option price is increased. That is totally against what you would see in a deterministic world. In a deterministic world, when you increase the interest rate, what you do is you decrease the present value of the cash flow. But here the cash flow hasn't changed, but we haven't decreased its present value. Its fair value is 15.64, which is an increase on 11.04. So this should tell you that option pricing can produce and throw up some interesting and surprising results. It is very different from the deterministic world, which you are probably more familiar with. Before we end this module, I want to spend a couple of minutes discussing the existence of risk-neutral probabilities and their implications for no arbitrage. First of all, recall our analysis of the binomial model. We saw there that no arbitrage is equivalent to D being less than or being less than U. We also saw that any derivative security with a time capital T payoff, CT, can be priced using risk-neutral pricing as follows, where Q and 1 minus Q are the risk-neutral probabilities and N is the number of periods. Just to relate N and T to you as follows, if you assume that delta T is the length of a period, then capital T equals N times delta T. So that's the link between T here and N over here. Okay, so this is what we saw in the binomial model. When there's no arbitrage, there are risk-neutral probabilities that are strictly positive, such that all cash flows and derivative securities can be priced using this representation here. This representation is actually more general. In fact, you can show that if there exists a risk-neutral probability or risk-neutral distribution Q such that 4 holds in any model, then arbitrage cannot exist. Okay, why is this the case? Just to see a simple example, consider the following situation. Suppose we've got a model with M states, omega 1, omega I, down to omega M. Okay, and suppose we want to consider some security which has a payoff in each of these states. And we'll assume that payoff is non-negative in all of these states. And let's suppose that there's actually one state where the payoff is strictly positive. Okay. Now, if we have risk-neutral probabilities, strictly positive risk-neutral probabilities, Q1, so on down to Qi, down to Qm, such that this situation is satisfied, then notice that the expected value of CT, so this is CT here, then the expected value of CT must be greater than 0. Why is that? Well, all of these probabilities are strictly positive. You're multiplying them by a cash flow that's non-negative, and at least in one state, strictly positive. Therefore, the expected value of CT is strictly positive. But what that means is that you can't get a type B arbitrage. That's not possible. Okay? Similarly, you can show that you can't get a type A arbitrage. Okay? You would just replace this with a greater than or equal to sign and show then that the price of this, according to the representation in 4, is greater than or equal to 0, which means it can't have a negative cost, which means there can't be a type A arbitrage. So in fact, any model which has this representation, in other words, where you can compute the value of CT using a set of risk-neutral probabilities, then in such a model there cannot be an arbitrage. Okay, the reverse actually is also true. If there is no arbitrage, then a risk-neutral distribution exists. We've shown that in the binomial model, but it's actually true more generally. And together, these two last statements are often called the first fundamental theorem of asset pricing. That is, the existence of risk-neutral probabilities and no arbitrage are equivalent. Up until this point, we've only seen how to price European options in the binomial model. We're now going to consider the case where the holder of the option has the ability to exercise early. Such an option is actually called an American option, and we'll see that we can also easily price these securities in our binomial model. So the only difference is that we must now also check if it's optimal to early exercise at each node. So if you recall the way we priced European options, we actually started at the end at t equals 3. Here we've got a 3-period binomial model. We began at the end, computed the payoff of the European option at t equals 3, and then we worked backwards 1 period at a time, figuring out how much the option was worth at each period, and working our way backwards using our 1-period results to get the option price at time 0. That's how we computed the European option prices. Well, we can do the exact same thing with American options. We're going to start at the end, and we're going to work backwards 1 period at a time using the risk-neutral probabilities in each period to compute the value of the option. The only difference is now we have to check at each period if it's optimal to exercise early. So when we're working backwards, we're going to compute the value of the option, but also check to see if that value is greater than the value of exercising at that point. If it is, we don't exercise. If it's not, we do exercise, and we continue backwards. Okay, and we're going to see how this works in practice. There's also a spreadsheet that you can use to see the calculations and to see how we price the American option. So if you like, you can go through that spreadsheet or have it open while we're doing these calculations. Okay. First of all, recall that it is never optimal to early exercise an American call option on a non-dividend paying stock. So we saw that in an earlier module. So we're actually going to consider pricing American put options here. So the put option is going to assume an expiration or a maturity of t equals 3, a strike of $100, and we'll assume the risk-free rate, the gross risk-free rate per period is 1.01. Okay, so this is our binomial model that we've been using a lot until now. It starts off at $100. The stock price starts at $100. It goes up by a factor of u. It goes down by a factor of d in each period. So the payoff of the put option, so remember the payoff of the put option will be the maximum of 0 and the strike minus the stock price at time 3. The stock price at time 3 is 81.63, 93.46, 107, and 122.5. The strike is 100. So we will only exercise if the security price is less than 100. So that's why we're going to get 0 up here, and we're going to get 100 minus 93.46 down here, and 100 minus 81.63, which is 18.37. So this is the payoff of the American option if we exercise at a time t equals 3. And all we're going to do to price this American option is we're going to work backwards in the same manner as we did with European options, but this time at each node we'll also have to check if it is optimal to exercise at that point or not. Okay, so here's an example of how we do these calculations. So we know the value of the American option at t equals 3. It's 0, 0, 6.54, 18.37. So we're going to work backwards 1 node at a time. So let's actually consider this piece here. And suppose we're down at this node here and we want to figure out how much is the option worth. Well, if it was a European option, we would say the fair value of the option is 1 over r times q times 6.54 plus 1 minus q times 18.37. That's how we computed the fair value of a European option in a 1-period model. We discounted and used the risk-neutral probabilities to compute the expected payoff 1 period ahead. We do the exact same thing here, except we have the ability to early exercise the option. In other words, when we're at this node, we have 2 choices. We can choose to continue, or we can exercise. The choice is ours. If we choose to continue, the fair value of the option is this guy here, whatever this turns out to be. Let's just call it x. So we'll get x. If we exercise, we'll get 100 minus 87.34, and that's equal to 12.66. However, the choice is ours. So we will choose to exercise if 12.66 is greater than x, and we will choose to continue if x is greater than 12.66. In this case, it turns out that 12.66 is the greater of the two, so x is less than 12.66. So at this node, we choose to exercise, and we get 12.66. So the fair value of the American option at this node is $12.66. And we do the exact same thing at this node and at this node. And as I said earlier, you can see these calculations in the spreadsheet that we've uploaded onto Coursera. Okay. So we can work backwards in each period, and we actually find that the fair value of the American option is 3.82. Okay. Not only that, you will see that the only point at which it is optimal to exercise early is down here at this node. At each of the other nodes, the fair value of the option turns out to be the continuation choice. It's only at this node that exercising was optimal, and that's why we've highlighted it in a different color here. So that's how we price American options. We just work backwards in the lattice, in the binomial tree, as we did with the European options, but with the added complication of having to check at each node whether it was optimal to exercise or not. To give ourselves a flavor of optimal stopping problems, we're going to consider one more example, and this is a simple die throwing game. So consider, for example, the following game. We've got a fair six-sided die. So let's try and draw a six-sided die. Okay. So we've got the numbers 1 to 6 on the 6 sides of this die. We're allowed to throw the die up to a maximum of 3 times. After any throw, you can choose to stop. And when you stop, you obtain an amount of money equal to the value you threw. So the value you threw is whatever is showing here when you throw the die. So for example, if you throw a 4 on your second throw and you choose to stop, then you'll obtain $4. So if you were risk neutral, how much would you pay to play this game? By risk neutral, I mean that you just want to compute the fair value of this game using the true probabilities. The amounts of money concerned are so small, the risk doesn't enter into the situation. Okay, so how much is this game worth playing? I always like this game because it gives you an example of another optimal stopping problem. It's also a game or a question that many interviewers over the years have liked to ask our students when they're interviewing for jobs in the financial industry. So let's think about this. So the solution is going to be to work backwards, starting with the last possible throw. So if we've just got one throw remaining, then the fair value of the game must be 3.5. And the reason is, on that last throw, you can get 1, 2, 3, 4, 5, or 6, each with probability 1/6. And so the fair value of this game is 1/6 times 1, 1/6 times 2, and so on, and it's equal to 3.5. Now, suppose you've got 2 throws remaining. What we must do is figure out a strategy which determines what to do after the first throw of these 2 throws. Okay, so that first throw refers to the first of the 2 throws remaining. So it's throw 2 in the overall game. Okay, so let's think about this. So we've got throw number 2. We can get a 1, a 2, a 3, a 4, a 5, or a 6 on that throw. Each of these occurs with probability 1/6. So if we get a 1, 2, or 3, if you think about it, it would make sense to continue. Why? Well, if we continue, we will expect to get 3.5 on our last throw. So why would you stop and get a 1, a 2, or a 3 when you expect to get a 3.5 on your last throw? So in each of these, you would continue and expect to get 3.5. On the other hand, if you get a 4, a 5, or a 6, then why would you continue? Why would you continue and expect to get a 3.5 when you can stop and get a bigger number? So in fact, for each of these numbers, you will stop and get 4, 5, or 6. So the fair value of the game with 2 throws remaining is 1/6 times 3.5 plus 1/6 times 3.5 plus 1/6 times 4 plus 1/6 times 5, and so on. So the fair value of the game is 1/6 times 4 plus 5 plus 6 plus 1/2 times 3.5, which is 4.25. So that's the fair value of the game if there's 2 throws remaining. If there's 3 throws remaining, the exact same idea works. You now consider the first throw. Okay, so there's not much room here, but the first throw we could start with here. And we would figure out what to do in each of these scenarios. Well, if we throw a 1, 2, 3, or 4, we would actually choose to continue. Why? Because the fair value of continuing with 2 throws remaining would be 4.25, which is greater than 4. Otherwise, if we get a 5 or 6, we would stop. So you can actually compute the fair value of this game. It's going to be 2/3 times 4.5 plus 1/6 times 5 plus 1/6 times 6. And that's the fair value of this die throwing game. If you could throw the die 1,000 times, what do you think will happen to the fair value of the game then? It should be pretty clear, and I'll let you think about that. The reason I like this game, though, is it emphasizes the idea of a strategy or a stopping time. You have to figure out the optimal strategy, what you must do at each point in time. Do you continue or do you stop? With the American option problem, you have to figure out, do you exercise or do you continue? In the binomial example over here, we did it automatically by working backwards, and at each point, at each node, we figured out the optimal strategy. Do we exercise or do we continue? And we got the fair value of the option, 3.82. In this module, we're going to discuss replicating strategies in the binomial model. We've already seen replicating strategies in the one-period binomial model, but we're actually going to see as well that we can construct replicating strategies that replicate the payoff of an option in the multi-period binomial model. And we'll see, in fact, that we can price options by constructing a replicating portfolio. In fact, that's what we were doing all along when we were computing option prices by working with the one-period risk-neutral probabilities and working backwards in the binomial lattice. They're actually the same thing, but we're going to make that clear in this module. We're going to, as usual, let ST denote the stock price at time t. We're now going to let BT denote the value of the cash account at time t. We haven't spoken about BT before, but it's always been there in the background where we spoke about the gross risk-free rate, R. So what we're going to do now is formally recognize that as a security. We're going to start off at time 0 with B0 equals $1. So this is the value of the cash account at time 0. And then the value of the cash account at time t is simply R to the power of t. So it's just a deterministic security that grows by a factor of R in each period. Okay, so now we're explicitly viewing the cash account as a security. We're going to let xt denote the number of shares held between times t minus 1 and t for each t equals 1 up to n. We're also going to let yt denote the number of units of the cash account that we hold between times t minus 1 and t for t equals 1 up to n. And then we're going to define theta t to be xtyt, and this is the portfolio that is held at time t. So it is the portfolio that's going to be held immediately after trading at time t minus 1 and immediately before trading at time t. So theta t is the portfolio that's held between times t minus 1 and t. Theta t is also a random process, and in particular we call this a trading strategy. So here's an example of a 3-period binomial model, and in this case we have theta 0 applying from this time to this time. Of course, we can have another theta 0 from this node down to this node. And of course, theta 0 is identical in both cases because it has been chosen at this time here and it can't look into the future when it's making its trading decisions. For another example, theta 2 will be chosen at this node. Theta 2 will be chosen at this node, theta 2 will be chosen at this node, and in each case the theta 2 will be actually different. So we'll have a different theta 2 here, a different theta 2 here, and a different theta 2 here, and of course theta 2 then applies at time t equals 3. Okay, so these are examples So this theta here is an example of a trading strategy. And of course, you'd also have a theta 1 chosen there and a theta 1 chosen there. And the particular amounts of securities of the security and the cash account that you purchased at time 1 will depend on whether you're down here or you're up here. Now I want to discuss the concept of self-financing, and in particular, self-financing trading strategies. Before we do that, we just need to define what we mean by the value process, Vt of theta, that is associated with a trading strategy, theta t equals xt yt. We define Vt to be equal to xt st plus yt bt for t greater than or equal to 1. And of course, this is just the value of the portfolio at time t. xt is the number of units of the stock that we hold, so xt st is our stock position, and yt bt is our position in the cash account, or value of our cash account position. So this is the total value of the portfolio. We need a slightly different definition of t equal to 0, and that's because we don't have an x0, y0. If you recall, xt is the number of units of shares that we purchase at time t minus 1. So if we had an x0, we would be referring to time minus 1, but we don't have a time minus 1. So we have a slightly different definition for t equal to 0, but we still end up with the value of the strategy at time 0. So when t equals 0, we get Vt equals x1 times s0 plus y1 times b0. But of course, x1 is chosen at time 0, and y1 is chosen at time 0. So if you like, this is the value of the portfolio immediately after trading at time 0. Okay, so that's the value process. We now want to define what we mean by a self-financing trading strategy. A self-financing trading strategy is a trading strategy where changes in Vt are due entirely to trading gains or losses, rather than the addition or withdrawal of cash funds. In particular, a self-financing trading strategy satisfies Vt equals xt plus 1 st plus yt plus 1 bt. And if you notice, Vt is therefore the value of the portfolio immediately after trading at time t, because xt plus 1 is the number of units of shares held between times t and t plus 1, and yt plus 1 is the number of units of the cash account held between times t and t plus 1. So this is the value of the portfolio immediately after trading at time t. Up here, this is the value of the portfolio immediately before trading at time t. We now have the following proposition. If a trading strategy theta t is self-financing, then the corresponding value process Vt satisfies this relationship here. So what's going on in this relationship here? Well, the left-hand side is just the change in value of the portfolio. And on the right-hand side, we have xt plus 1, which is the number of units of the share held between times t and t plus 1, times the gain on the stock, plus yt plus 1 times the gain on the cash account. So all this is saying is that if a strategy theta t is self-financing, then the gain on the portfolio is equal to the number of stocks held times the gain on the stock plus number of units of the cash account times the gain on the cash account. So in particular, changes in the value of the portfolio can only be due to capital gains. So gain in the stock or gain in the cash account or capital losses, and not the injection or withdrawal of funds. In other words, nobody is injecting funds into the portfolio at time t or t plus 1, and nobody is withdrawing funds from the portfolio at times t or plus 1. So all the changes in the value of the portfolio are coming from capital gains or losses on the stock and cash account. And it's actually easy to check this result. So we'll just go through it for the case t is greater than or equal to 1. In that case, Vt plus 1 minus Vt is as follows. Well, Vt plus 1 is actually equal to, we can see it here, it is equal to, we're going to use this definition at t plus 1, so it's xt plus 1 st plus 1 plus yt plus 1 bt plus 1. So that's what this term is here. And when we subtract Vt, we're going to use the self-financing condition and use this over here. And that's this term here. You put them together and you get the desired quantity. We get a similar simple proof for the case where t equals 0. So that's what a self-financing trading strategy is. It's a very intuitive idea. It's simply what you would get from a trading strategy where all the trades are funded by the gains or losses in the portfolio through time. And they're not funded by injecting fresh capital into the portfolio or taking capital out of the portfolio. Okay, in this slide, I want to talk about risk-neutral prices of securities and emphasize that, in fact, they're the same thing. Those prices are the same prices you get from constructing replicating strategies. Okay. So we have seen how to price derivative securities in the binomial model, and the key we saw to this was the use of one-period risk-neutral probabilities. But actually, we first priced options in the one-period models using a replicating portfolio argument. And we did this without ever needing to define risk-neutral probabilities. If you go back to that earlier module, you'll see we actually priced the one-period option by constructing a replicating portfolio. We only constructed risk-neutral probabilities afterwards, and we used these risk-neutral probabilities then to price all securities. But the first thing we did was we constructed a replicating portfolio in the one-period model. Well, in the multi-period model, we can do the same. We can construct a self-financing trading strategy that replicates the payoff of the option. This is called dynamic replication. And the initial cost of this replicating strategy must equal the value of the option. Otherwise, there's an arbitrage opportunity. And the way to see this is as follows. So as before, let theta t be our self-financing trading strategy. Let V0 be the initial value of the strategy. And let V capital T be the terminal value of the strategy, or Vn. We've been using n for number of periods, so we can stick with n. Now, because this is a self-financing strategy, there are no cash flows between time 0, which I'll highlight here. There are no cash flows between time 0 and time n. There's no cash flow coming out, there's no cash flow going in. The strategy self-finances itself. So the only time there's a cash flow is at time 0, which is when the portfolio is constructed, and at time n it has some value. So if Vn is equal to the value of an option, say at time n, Cn, then the fair value of the option at time 0 must be V0. Otherwise, there would be an arbitrage strategy. For example, if V0 was less than C0, you could buy V0, buy the self-financing trading strategy at time 0, sell the option at time 0, so you would make money for nothing. You would get C0 minus V0, which is greater than 0. And then at maturity at time n, Vn would be equal to Cn, so the cash flows would cancel each other out at time n, and that would be an arbitrage. Okay, so the initial cost of this replicating strategy must equal the value of the option. This dynamic replication price is, of course, equal to the price obtained from using the risk-neutral probabilities and working backwards in the binomial lattice. And at any node, the value of the option is equal to the value of the replicating portfolio at that node. So, for example, this is our earlier European option. So in black, here we have the stock price. In blue, we have the option price. And in red, XTYT, we have the replicating strategy. So the way we priced this option initially was we determined the payoff at time t equals 3. Remember, the strike here was $100. So it was a call option with strike equals $100. So these are the payoffs of the options, 22.5700. And the way we priced this option originally was we computed its price at time t equal to 2 by looking at each of the one-period models at time t equals 2. So this is one period model, this is another one-period model, and this up here is another one-period model. And we used our one-period knowledge, in particular the one-period risk-neutral probabilities, to compute the prices of the option at these points. Okay, and then given these prices at time t equals 2, we work backwards to t equals 1 to compute the price of the option at t equals 1, again using our knowledge of one-period binomial models and the one-period risk-neutral probabilities. So for example, here we found that the price was 10.23, and in fact 10.23 was calculated as the price of a derivative security that paid 15.48 at this node and 3.86 at this node, i.e. the value of the option at this node and the value of the option at this node. But in fact, when we're doing that, all we're really doing implicitly is constructing the strategy at this point which replicates 15.48 and 3.86. So when we were working backwards in the lattice, what we were really doing is constructing a replicating self-financing trading strategy. Okay, so we can see here in the next slide, we can see the replicating strategy. Modulo rounding errors, there's not enough, if I put in additional decimal points, the slide would look too cluttered. So modulo rounding errors, these numbers are correct. So XTYT, XTYT. And what you can actually see, for example, down here we have it. So 0.8, so now I'm referring to this node here. Okay, so at this node here, what we are saying is that 0.802 times 107, 107 is the value of the stock at that time, minus 74.84 times 1.01, well, this is the value of the cash account at time 1 and at this node. Well, that's equal to 10.23, which is the value of the option at that node. And you can check that this strategy actually at time 2 will replicate 15.48 if the stock price goes up, if we go up this way, or the strategy will be worth 3.86 if the stock price falls. Another check you can do here is you can actually check the self-financing condition. So here's how we can do that. So the self-financing condition at this node should say that the value of the portfolio just before trading at this node equals the value of the portfolio just after trading at this node. So just before, what is the value of the portfolio? Well, just before trading, we're holding 0.598 units of stock, and the stock is worth 107. And we are short minus 53.25. times the cash account, which is worth 1.01 at that node. So this is the value of the portfolio just before trading at this node. Just after trading at that node, we are holding 0.802 units of the stock and minus 74.84 units of the cash account. And as I said, modular rounding errors, these two numbers must be the same. That is the self-financing condition. So when you look at option pricing in this binomial model, you can think of it as using the risk-neutral probabilities, working backwards one period at a time to compute the price. But what you're also implicitly doing when you do that is you're constructing the self-financing trading strategy that replicates the payoff of the option. And the value of the self-financing trading strategy at time 0 is 6.57. And this is called dynamic replication. What you're doing is you're using a trading strategy which adjusts the holdings in the stock and the cash account at each time so that at time t equals 3, at maturity, we replicate the payoff of the option. So far we've discussed option pricing and derivatives pricing in the binomial model, but we've made no mention of dividends. In this module we're going to discuss dividends and point out that it's actually easy to include dividends in the binomial model. So here's our one-period binomial model again. We start off at t equals 0 with the security price of S0. We have a probability of P, a true probability of P, and a true probability of 1 minus P of an up move and down move respectively. We're going to assume that if the security goes up, the value of the stock goes to US0, and if it goes down, it goes to DS0. But we're also going to assume that the security pays a proportional dividend of C times S0. And at C times S0 is what gets paid out as a dividend at time t equals 1, regardless of whether the stock has gone up or down. So you'll see that CS0 is here and CS0 is down here as well. So this is the dividend that gets paid out to the shareholders. Okay. As before, we have a cash account which pays out a gross risk-free rate of R. We assume the cash account is worth $1 or €1 or 1 whatever at time t equals 0, and it's worth R at time t equals 1. So it's easy to check again that there are no arbitrage conditions for this one-period binomial model, and in particular the no arbitrage conditions are given to us by here. And this is the direct analog of the no arbitrage conditions we saw when there were no dividends. So D plus C is the total return on the stock if the stock falls from S0 to DS0, and U plus C is the total return on the stock if the stock rises from S0 to US0. So clearly R cannot be less than D plus C, otherwise there would be an arbitrage. You could buy the stock and sell the cash account. Likewise, if R was greater than U plus C, then you could short sell the stock and buy the cash account and again create an arbitrage. Okay. So what we can do is, if suppose we want to price a derivative security with value C1 of S1 at time 1, it pays off CU in this upper state here, and it pays off CD in this lower state over here. So what we can do is we can again construct our one-period replicating strategy to replicate the payoff of this option. So in particular, we're going to let X be the number of units of the stock that we purchase at time 0, and Y be the number of units of the cash account that we purchase at time 0. Well, then the replicating aspect of this portfolio means that we must have these two linear equations. In particular, the value of the portfolio here on the left-hand side, if the stock goes up, is US0 times X plus CS0 times X. So this is the dividend piece, this is the value of the stock, plus R times Y, this is the position in the cash account. And that must be equal to C0 if the stock price goes up. If the stock price goes down, then we have DS0X plus CS0X plus RY equals CD. So these are the two equations that we have. If we can find X and Y so that these two equations are satisfied, then the portfolio XY, which is purchased at time 0, replicates the payoff C0 and CD. So therefore, the value of this portfolio at time 0 must be the arbitrage-free value of this derivative security. So we can solve these two equations and two unknowns. If we do that, we'll find that C0 can be written as follows. The fair value C0 is equal to XS0 plus Y, and we can write it like this. Again, we can write it in the form of having risk-neutral probabilities, and now Q is equal to this quantity here, which is the same as our original one-period risk-neutral probability, except now we have this additional minus C. 1 minus Q is equal to U plus C minus R divided by U minus D, and that's that term there. So again, when the security pays a proportional dividend, we can still construct a replicating strategy, and we can compute the price of a derivative security as the discounted expected terminal payoff of the derivative security using these risk-neutral probabilities. Okay. In the multi-period binomial model, we can assume a proportional dividend is paid in each period. In particular, we would assume a proportional dividend of CSI is paid at t equals I plus 1. Then each embedded one-period model has identical risk-neutral probabilities. They're given to us by these quantities here, and derivative securities are priced as before. We can work backwards in the binomial lattice using these risk-neutral probabilities to calculate the fair value or arbitrage-free value of the derivative at each time period until we get back to t equals 0, which gives us the initial price, arbitrage-free price of the security. In practice, dividends are not paid in every period. They're often paid every 6 months or every year, and so they're a little more awkward to handle in practice. We might discuss that later in the course, but for now we'll leave it at that point. Another point to keep in mind is the following. Suppose the underlying security does not pay dividends. Then it's easy to check that this is true. The initial value of the stock is equal to the expected value using the risk-neutral probabilities of the terminal value of the stock discounted. And of course, that follows easily from our risk-neutral pricing because we know that the stock price is equal to Sn minus 0, 0, take the max of these two. So in fact, this is just a call option with k equal to 0. So a stock price is equal to a call option on the stock with strike k equal to 0. And so this just follows from our pricing of call options. But of course, every security must be priced like this. Okay. suppose now that the underlying security pays dividends in each time period. Then you can check that A no longer holds. Instead, what holds actually is the following. The initial value of the stock, S0, is equal to the expected value at time 0 using the risk-neutral probabilities of Sn divided by R to n, which is what we had here, plus the sum of the dividends, which we'll call DI, discounted appropriately. Okay? We're assuming Sn is the ex-dividend security price at time n. So Sn is the price at time n immediately after the dividend at time n is paid. And you don't need any new theory to prove this. We can just use what we've seen already. It follows from risk-neutral pricing and observing that dividends and Sn may be viewed as a portfolio of securities. So to see this, we can view the ith dividend as a separate security with value equal to this quantity here. So if we view the ith dividend, which is paid at time I, as a security, it pays a cash flow only at time I, then our risk-neutral pricing tells us that the value of this dividend is Pi, and it's equal to this quantity here. Now we can view the owner of the underlying security as owning a portfolio of securities at time 0. The value of this portfolio is the value of the securities within the portfolio. Those securities are each of the n dividends, okay, and each of those n dividends is value Pi for I equals 1 to n, plus the terminal value of the stock, or if you like, the value at time n, and that's Sn discounted by R to the n, taking its expectation with respect to the risk-neutral probabilities. But of course, we also know that the value of the underlying security is S0. So S0 must be equal to this quantity here. Okay? And so we get S0 equals to the sum of the PIs plus this quantity, and that is just equation 9. We're now going to see how to price forwards and futures in the binomial model. We'll see that they're very straightforward to price, even though the mechanics of these securities are different. We'll also ask the question, how do the prices of forwards compare with the prices of futures? We'll see that in the binomial model, they're actually identical, although we will make the point that this is not true in general. We're going to start with an n-period binomial model, although in this case we see n is just equal to 3. U equals 1 over d as usual. And of course we also have our usual cash account, which pays a gross risk-free rate of R in each period. Okay, so consider now a forward contract on the stock that expires after n periods. We're going to let G0 denote the date t equals 0 price of the contract. Now, I have price in quotes here because there's often a lot of confusion over the word price, because people sometimes think that if something is a price, then that is what you must pay to purchase the contract. But of course, that is not true. G0 is chosen so that the contract is initially worth 0. So therefore, when you buy a forward contract, no money changes hands. In fact, the initial value of the forward contract is 0. The so-called forward price here, G0, is just used to determine the payoff at the maturity of the forward contract. There's also a similar situation with futures, which we'll discuss when we come to the pricing of futures in the binomial model in a few minutes' time. Okay, so back to the forward contract. G0 is the price of the contract, but actually the value of the contract when we enter into it is 0. So, using risk-neutral pricing, the initial value of the contract is 0. That's how much we must pay if we buy this forward contract. We get nothing until time n, and at that point we get Sn minus G0. This is the payoff of the forward contract. So therefore, risk-neutral pricing says that 0 is equal to the expected value using the risk-neutral probabilities of the payoff discounted, and the discount factor is R to the power of n. So this is simply risk-neutral pricing. Okay, now what we must do is we need to figure out what is G0. That's the goal here, to figure out the fair value of G0. We will do this by just looking at this equation. We notice, first of all, that Rn is a constant. Okay, the gross risk-free rate is a constant, so it comes outside the expectation. And so we actually just get 0 equals the expected value of Sn minus G0. Remember, G0 is also a constant. It's chosen at time 0. So it is not a random quantity, so we don't have an expectation around it. So, of course, this implies G0 is equal to this. And this is the forward price of the contract. Okay. And 10 holds whether or not the underlying security pays dividends. We've now discussed dividends in the context of the binomial model. We didn't mention dividends at all here, but in fact, dividends can be present in the model, and this is still the correct price. The only point where dividends will enter is in Q. Okay, if you remember, the risk-neutral probabilities Q are given to us by, it's going to be R minus D minus C divided by U minus D. Okay, and so if the underlying security pays dividends, well, this is going to enter into the risk-neutral probability. It will lower the risk-neutral probability of up moves and make the forward contract a little cheaper than would otherwise be the case. Okay. And it will make the forward contract a little cheaper than would be the case if dividends were not present. Okay, futures. Consider now a futures contract on the stock that expires after n periods. Okay, let FT denote the day T price of the futures contract. And again, I put price in quotes because FT isn't the value of the futures contract. Right? If we enter into a futures contract at any time, it actually costs nothing. The fair value of a futures contract at any time is actually 0. Okay? So, as was the case with the forward contract, this futures price is really used to determine the payoffs of owning a futures contract. So we'll come to that in a moment when we actually price the futures contract. Okay, so the futures contract expires after n periods, so therefore we know Fn equals Sn. This is almost by definition. These would be the terms of the futures contract. It expires at time n, and according to the rules of the contract, Fn is equal to Sn. So this must be the case. Okay. So as I mentioned earlier, a common misconception is that FT is how much you must pay at time t to buy one contract, or how much you receive if you sell one contract. This is false. A futures contract always costs nothing. The price FT is only used to determine the cash flow associated with holding the contract. So that plus or minus FT minus 1 is the payoff received at time t from a long or short position of one contract held between times t minus 1 and t. So it would be plus FT minus 1 if we were long or we owned one futures contract, and it would be minus if we were short or we had sold one futures contract between times t minus 1 and t. So in fact, some people will often characterize a futures contract as follows. They will say that a futures contract is a security that is always worth 0, but that pays a dividend. I should put quotes here. It's not a dividend like the dividend you get from a stock. So it pays a dividend of FT minus 1 at each time t. And of course, this quantity here can be greater than or equal to 0 like a regular dividend, but it can also be less than 0. Okay? So you can think of a futures contract as being a security that's always worth 0. After all, it never costs you anything to purchase or sell a futures contract, but it does create a stream of payoffs afterwards. And these payoffs can be thought of as dividends or generalized dividends, and these dividends are given to us by this quantity here. Okay, how do we price a futures contract in the binomial model? Well, we're going to work backwards from time n, the maturity of the futures contract. So we know it costs nothing to enter into a futures contract at time n minus 1. So 0 is the initial value of the futures contract. As I said in the previous slide, a futures contract is always worth 0. So using the one-period risk-neutral pricing, that's all we're using here. One-period risk-neutral pricing says 0 is equal to the payoff of the futures contract at maturity, which is time n, and that payoff is Fn minus 1. We discount by R, and we see 0 equals this using the risk-neutral probabilities. Okay. From this, we get Fn minus 1 is equal to the expected value of Fn using the risk-neutral probabilities and conditioning on time n minus 1 information. This follows because R is a constant, so it comes outside and it disappears, and Fn minus 1 is known to us at time n minus 1. So in fact, Fn minus 1 doesn't need an expectation around it at all. So therefore we have Fn minus 1 equals the expected value of the futures price 1 period ahead using the risk-neutral probabilities. We can generalize this to any time t and t plus 1 and get the exact same relationship using the exact same argument to get this relationship here. Okay, so this is the relationship for general t. Okay, now we can also recognize the fact that ft plus 1 is equal to the expected value at time t plus 1 of ft plus 2. That's just using this relationship, but taking t equal to t plus 1 inside here, we get this. So we can substitute this in for ft plus 1 to get this quantity here. And we can keep doing the same thing. We know ft plus 2 is equal to the expected value at time t plus 2 of f t plus 3, and we can substitute that in for ft plus 2 and so on, and we get up to this point here. Then we can use what's called the law of iterated expectations, and the law of iterated expectations just tells us that we can collapse all of these expectations just into the expected value of at time t under q of fn. Okay, so that's what the law of iterated expectations tells us. You should be familiar from this from some of your probability courses. If not, you don't have to worry about it. We're not going to be using it too much during this course, and it certainly won't appear in any of the assignments. Okay, so the law of iterated expectations tells us that ft equals the expected value of fn, conditional on time t information using the risk-neutral probabilities q. So in fact, ft is what's called a q martingale, and indeed we've recorded an additional module which introduces us to martingales, and that module can be found on the course website as well, if you're not familiar with the idea of a martingale. Okay, so we can take t equal to 0, recognize the fact that fn equals Sn by the definition of the futures contract. So therefore we find f0 equals the expected value of Sn at time 0 using the risk-neutral probabilities. And again, this holds irrespective of whether or not the security pays dividends. The dividends would only enter into the calculation of the risk-neutral probabilities Q, as I mentioned a few moments ago. What's interesting to ask at this point is, are the forwards and futures prices equal? And yes, they are. You can see this expression in 11 is identical to the expression we have in 10 as well. So even though they're different contracts, the futures marks to market every day. There's a payoff every day, that dividend payoff we spoke about, whereas a forward contract pays nothing every day until maturity. They actually have the same price. F0 equals E0 of Sn using the risk-neutral probabilities Q. This is not true in general. It's only true in the binomial model and other certain types of models. The reason it holds true here, in fact, is if you were to go back and look at these slides, you would see one of the reasons it's true is when interest rates are deterministic. So interest rates are deterministic, so we were able to take this R outside and go through the rest of the analysis and see that we got the futures price equal to the forward price. In general, interest rates are actually random. They move about through time. And as a result, you wouldn't be able to take this Rn outside. And so in models that have random interest rates, you would find that futures prices and forward prices are not identical. They would be very similar, but they wouldn't be identical. In this module, we're going to briefly discuss the Black-Scholes formula. The Black-Scholes formula is of great significance. It's used an awful lot in industry. And indeed, we can view the binomial model as an approximation to the Black-Scholes formula. Black and Scholes assumed a continuously compounded interest rate of R, so that $1 invested in the cash account at time 0 would be worth e to the RT dollars at time t. They also assumed geometric Brownian motion dynamics for the stock price, so that the stock price at time little t is equal to the initial stock price times the exponential of this quantity here, where Wt is a standard Brownian motion. And for those of you who are interested, we have recorded separate modules on both Brownian motion and geometric Brownian motion. These modules are available on the course website. They also assume that the stock pays a dividend yield of C. They assumed continuous trading with no transactions costs, and they also assumed that short selling was allowed. So here are some sample paths of geometric Brownian motion. They look quite similar to sample paths of Brownian motion, actually. you can see that the stock price never jumps here. So at no point you see the stock price, say, jumping from here down to here. So that's a property of Brownian motion and geometric Brownian motion. The sample paths are actually continuous. Given the assumptions that Black and Scholes made and that we listed 2 slides ago, they succeeded in deriving the price for a European call option with strike K and maturity T. It is given to us by this quantity here. It's a somewhat complicated looking formula, but it's easy to code up, and it is used everywhere in industry today. The interesting thing to note about this formula is that mu, which was the drift of the geometric Brownian motion 2 slides ago, so recall we assumed a drift of mu here. Well, if you notice over in the Black-Scholes formula, mu does not appear anywhere. And this is similar to the fact that P did not appear in the option pricing formulas we derived in the context of the binomial model. We'll return to that in a moment. So European put option prices, P0, can then be calculated from put-call parity. So once we have the call option price up here, we can price put options. In other words, we can derive P0 using put-call parity here. And this is the version of put-call parity that applies when we have a dividend yield. Black and Scholes obtained their formula using a similar replicating strategy argument to the one that we used for the binomial model. In fact, you can show that under the Black-Scholes geometric Brownian motion model that we can write the price of the option C0 as being the expected discounted payoff of the option using risk-neutral probabilities Q. This is exactly the same formula we had for the binomial model. In this case, however, in the continuous time model of geometric Brownian motion, under Q, we assume that the stock price is given to us by this here. And the only difference between this expression for ST and the expression we had for ST a couple of slides ago, which was mu minus sigma squared over 2 times T plus sigma WT, is that we now have a factor or minus C appearing here, which we don't have down here. And the true drift of the geometric Brownian motion mu no longer appears in the option pricing formula. This is exactly analogous to the fact that we used the risk-neutral probabilities Q and not the true probabilities P when we were pricing options in the binomial model. So in fact, if you evaluate this expectation, assuming ST is equal to this, you'll get the Black-Scholes formula. And for those of you who are interested, it's actually not very difficult to do this. It involves an integral of a log normal distribution. ST here will have a log normal distribution, so one can actually evaluate this, do some integration, and actually get the Black-Scholes formula that we showed on the previous slide. The Black-Scholes formula is used a great deal in industry. In fact, it is the way in which option prices are actually quoted by industry practitioners. The binomial model is often used as an approximation to the Black-Scholes model, in which case one needs to translate the Black-Scholes parameters, or sigma and so on, into our familiar binomial model parameters. This is often referred to as the calibration of a binomial model. So suppose we're given some Black-Scholes parameters. We have R and we have sigma. And if you notice over here, that's all we need. We have R, we have sigma, we also have C, of course. And we'll see how to calibrate these and rewrite these parameters in our binomial model. So what we'll do is we will write Rn, and now we're going to have subscript n here to denote the fact that these parameters in the binomial model will depend on the number of periods that we're using in our binomial model. So recall, if t is the maturity of the option, then t is equal to n times delta t, where delta t is the length of a period in the binomial model. Okay, so we're going to assume that Rn is equal to e to the rt over n, where n is the number of periods, as we said. We'll assume that Rn minus Cn, so this is Rn minus Cn in the binomial model, will be equal to e to the r minus c times t over n. And a simple first-order Taylor expansion will tell you that this is approximately equal to 1 plus r t over n minus c t over n. So this, of course, is like our r factor, and this is our c factor in the binomial model. We'll set un equal to this and dn equal to 1 over un. And now we can price European and American options and futures and so on as before in the binomial model using these parameters. The risk-neutral probabilities will be calculated as Q subscript n. Again, recognize the dependence of our parameters on n, the number of periods. So Q subscript n will be equal to this here. And using this approximation, we can see that this is approximately equal to our Rn minus Cn minus Dn divided by Un minus Dn. So this is the representation of the risk-neutral probabilities that we saw before in the binomial model. We're actually going to use this in our binomial model now when we're deriving our parameters from a geometric Brownian motion and the Black-Scholes formula. So our spreadsheet will actually calculate binomial parameters this way. I mentioned at the beginning of the module that the binomial model can be viewed as an approximation to geometric Brownian motion. This is true as delta t, the length of a period, goes to 0. I'm just going to spend a couple of moments describing how you might go about showing this. We certainly won't go through all the calculations, but I'll do the first couple of steps of these calculations. Recall that we can calculate European option prices with strike K according to this expression here. So this is the expression we had in our binomial model. C0 equals the discount factor times the expected payoff of the option using the risk-neutral probabilities Q. Well, if you recall, we also saw that we can write this expression as we have written here. So these are the binomial probabilities. Okay, so this here is equal to the probability in our binomial model of J up moves and N minus J down moves. And this then is ST, the terminal stock price, after the J up moves and N minus J down moves. So therefore, this here is the expected value of the payoff of the option. So what you can do is we can actually replace this summation, which runs from J equals 0, to run from J equals, let's call it eta, say, where eta is the minimum J such that the stock price, again, this is ST, after J up moves and N minus J down moves. So eta is the minimum number of up moves required to ensure that the stock price is greater than or equal to K. In that case, this maximum will always occur in the first argument here. So we can remove the max, remove the 0, and just substitute this expression in here inside the summation, and then we can split the summation up into two components as we've done here. So what you have is we can rewrite in the binomial model, we can write C0, the initial value of the option, as being equal to S0 times some quantity minus K times some quantity. And if you recall, that's exactly what you had in our expression for the Black-Scholes formula. We had S0 times some quantity minus K times some quantity. What you can do, and we won't do it, but you can show that if n goes to infinity, or equivalently if delta t goes to 0, remember capital T is fixed, so if n goes to infinity, delta t goes to 0. You can show that if n goes to infinity, then C0, as we have here, will actually converge to the Black-Scholes formula. Very briefly, there is some great history associated with the modeling of Brownian motion and geometric Brownian motion, stochastic calculus, and finance and the pricing of options. There are many famous names, both mathematicians and economists, who are associated with this history. You might want to take a look at some of these names in your spare time. I'll just throw out a couple of very interesting people. Bachelier back in 1900 was perhaps the first to model Brownian motion. He was attempting to do so with a view to pricing options on the Paris Stock Exchange. Another fascinating person is Dublin, another French mathematician whose work was only recently discovered. He was actually very involved in the development of stochastic calculus, but his work wasn't discovered until very recently, as he died in World War II before his work could be read. Another very influential person or fascinating person is Ed Thorpe. Ed Thorpe is famous for card counting and showing that you can actually card count and beat the system in Las Vegas. After he was thrown out of Vegas, apparently he started trading options and may well have been the first person to actually discover and use the Black-Scholes formula. He didn't actually prove it was true. He didn't have a model which derived the Black-Scholes formula, but it seems like he somehow intuited that that might have been the correct formula for pricing options. And there's a host of other interesting names here that are well worth exploring. In this module, we're going to go through an example very quickly where we price a European put on a futures contract. Up until now, we've seen how to price European and American options on the underlying security. Very often, in fact, though, we want to price options on futures contracts, which are written on the underlying security. So, in fact, many of the most liquid options are options on futures contracts. They include, for example, the S&P 500 index in the US, the Eurostoxx 50 index in the Eurozone, the FTSE 100 from the UK, and the Nikkei 225 from Japan. In these cases, the underlying security is not actually traded. That is because if we wanted to actually trade the S&P 500, we would need to trade 500 different stocks, and that would be very expensive and time-consuming. So generally, we don't trade these indices, we trade futures on these indices. So what we're going to do is we're going to price a European put on a futures contract. So consider the following parameters. We're going to assume the initial stock price, or in this case the initial index price, is 100. We'll assume n equals 10 periods. We will assume a risk-free rate of 2%, a dividend yield of 1%, and a sigma of 20%. We're going to assume that the futures expiration and the option expiration coincide and are equal to 0.5 years. In practice, this is what typically happens. But of course, from our theory, we could, if we liked, still price options where the futures expiration was greater than the option expiration. We'll be able to obtain the futures price lattice on our spreadsheet by using the fact that Sn equals Fn, and then using the fact that for t less than n, Ft is equal to the expected value of Ft plus 1 using the risk-neutral probabilities. When we do that, we'll see that we get a put option value of 5.21. So let's go to the spreadsheet and see what we get. So here are our initial parameters. We have an initial price of 100, t equals 0.5 years or 6 months, sigma equals 20%, we're assuming 10 periods, and we have our R and dividend yield as well. So U, D, and Q are calculated as we showed in an earlier module where we used the binomial model to approximate geometric Brownian motion and the Black-Scholes model. So our futures parameters, we're assuming an expiration of t equals 10, so 10 time periods corresponding with 6 months or half a year. Over here, we can choose what sort of option we want to price. 1 for a call, minus 1 for a put. We're assuming a strike of 100, and the expiration again is going to be 10 periods. So the option expiration coincides with the futures expiration. It's going to be a European option. So here we have our lattice, or stock price lattice. In each time period, the stock price grows by a factor of U, or it falls by a factor of D. If we scroll down, we have the futures lattice. And in this case, we can see, well, by definition, Fn equals Sn at time n. So we see that the futures prices in here at time t equals 10 agree with the stock prices up here at time t equals 10. We then work backwards in this lattice, calculating the futures prices using that formula we showed on this last slide. Okay, so now we have our futures price lattice. We can now price our options by simply calculating the payoff of the option at time t equals 10, the expiration. So in this case, it's a put option with strike 100. So when the stock price is greater than 100, the payoff is 0. When it's less than 100, we get a payoff of 100 minus the stock price. So that gives us these values here. And then we can calculate the option by working backwards in the binomial lattice as we've seen before. In this case, we find the put option value is equal to $5.212. It's worth making a point about how these models are used in practice. In practice, we don't need a model to price liquid options. Market forces, i.e. supply and demand, actually determines the price of options. In this case, this amounts to determining sigma, or the implied volatility. And that is because, if you recall, so the price of a call option C0 is equal to the expected value at time 0 using our risk-neutral probabilities of e to the minus RT times st minus k, the positive part, or if you like, this is equal to the maximum of st minus k and 0, where under the Black-Scholes model, st equals s0 e to the r minus sigma squared over 2 times t plus sigma wt. Wt here is our standard Brownian motion. So W capital T is a random variable. It's got a normal distribution with mean 0 and variance t. Anyway, given all of this, we recognize that C0 is equal to some function of the initial stock price, the risk-free rate, the dividend yield, and I should have included the dividend yield up there, sigma, the time to maturity, and K. And in fact, we actually know all of these quantities. We can see them all in the marketplace. We know what S0 is, we know what R is, we know what the dividend yield is, we know what the maturity of the option is, and we know what the strike of the option is. The only thing we don't know is sigma. However, in the case of liquid options, we can actually observe C0, the price of the option in the marketplace. As I said, supply and demand is what really sets the price of liquid options in the marketplace. So we can see C0, and then we can use this equation to back out the one unknown, which is sigma. And then this is often called the implied volatility. And we'll be returning to this later in the course as well. So at this point, you might ask, if that's the case, if supply and demand sets the price of options, why do we need a model? Well, we need models for two reasons. One is to help us price what are called exotic or more illiquid derivative securities whose prices are not available in the marketplace. We can also use models to hedge options, and I'll return to hedging later in the course as well.